Think about the invisible infrastructure that powers the modern internet. It is not just the code you write or the algorithms that learn. It is the memory beneath it all. Every time you ask a question to an AI, a request is processed, a token is generated, and a massive amount of data is allocated and freed in milliseconds. If the memory manager fails, the latency spikes. If the memory manager fragments, the throughput drops. For a company like Meta, which operates at a scale few others can comprehend, standard memory management tools simply do not cut it. This is why there has been a renewed focus on jemalloc, the high-performance memory allocator, and a strategic pivot toward deep customization. Here's the thing about memory allocation. It sounds boring until it breaks. When you use the standard C library allocator, often called glibc malloc, it is designed to be a safe default. It works well for general-purpose applications. But in high-performance inference pipelines, that safety becomes a liability. The standard allocator uses a single global lock for thread safety. When thousands of threads are trying to allocate memory simultaneously, they end up waiting in line. This contention creates latency spikes that are unacceptable for real-time inference. Furthermore, standard allocators are prone to fragmentation. Over time, small pieces of memory get scattered across the heap, leaving large gaps that cannot be used even though the total free memory is sufficient. This leads to the dreaded out-of-memory errors despite plenty of available RAM. Meta has recognized that these bottlenecks are no longer theoretical. They are critical performance constraints that necessitate a return to foundational infrastructure improvements. The decision to invest heavily in jemalloc reflects a broader industry trend where high-performance systems prioritize fine-grained control over memory fragmentation and latency. This is not just about swapping one library for another, it is about rethinking how memory is managed at the lowest level. The renewed commitment signals a strategic pivot from reliance on external allocators to a deeply integrated, custom-built memory management solution optimized for their specific workload patterns. Let us look at how this works in practice. Jemalloc is designed with multiple arenas. Each arena can be assigned to a specific thread or core. This means that when a thread requests memory, it does not need to acquire a global lock. It talks directly to its own arena. This eliminates the contention that plagues glibc malloc in multi-threaded environments. But the real magic happens in the configuration. Meta has tuned these configurations to match their inference workloads. They utilize specific flags to control size classes. This means that instead of requesting arbitrary sizes, the system rounds requests to predefined buckets. This reduces internal fragmentation significantly. It also enables the system to reuse memory blocks more efficiently, reducing the need to ask the operating system for more physical memory. Consider the difference in behavior during a traffic spike. With a standard allocator, the system might struggle to find contiguous blocks of memory as the heap becomes fragmented. The garbage collection pauses, or the allocation delays become visible to the end user. With a tuned jemalloc configuration, the system manages these small and large allocations with precision. The heap fragmentation strategies are aggressive. Memory is returned to the operating system more frequently when it is idle, keeping the footprint tight. But when the system is under load, it keeps memory locally available to avoid the latency of system calls. This is the kind of optimization that separates a prototype from a production system. The industry has been moving in this direction for some time. Modern allocators face performance challenges in specific workloads, and the consensus is that a one-size-fits-all standard library allocator is insufficient. For massive-scale multi-threaded applications, custom or heavily tuned allocators are essential for maintaining throughput. Meta's internal optimizations suggest that they are pushing this even further. There are indications that formal verification efforts are being applied to memory management logic. Concepts seen in research like star malloc, which focus on formally verified, concurrent, and security-oriented memory allocation, are likely influencing their internal standards. This implies that the next generation of open-source allocator standards will be driven by how large-scale distributed systems handle concurrency and security. It is important to understand why this matters beyond just Meta. The renewed focus indicates that existing memory allocation bottlenecks have become critical performance constraints. As artificial intelligence models grow larger and more complex, the memory bandwidth and allocation latency become the limiting factors. If the software stack cannot manage memory efficiently, the hardware becomes underutilized. By investing in jemalloc, Meta is not just solving a bug, they are securing the foundation of their infrastructure. This allows them to run more models on the same hardware or run them faster, which directly impacts the cost and speed of their services. The implications for the rest of the industry are significant. When a company of this scale commits to a specific strategy, it often forces the ecosystem to adapt. If Meta proves that a heavily tuned jemalloc configuration yields better latency than glibc, other companies will follow. This drives the next generation of open-source allocator standards. It influences how large-scale distributed systems handle concurrency and security. We are seeing a shift where engineering complexity is accepted as a necessary cost for performance. The trade-off is no longer just about speed versus safety. It is about speed versus maintainability, and the decision is that for critical infrastructure, speed and control win. For developers working on high-performance systems, the actionable takeaway is clear. You cannot rely on the standard library allocator for everything. If you are building systems that require low latency and high throughput, you must consider the memory allocator as a first-class citizen of your architecture. You need to understand fragmentation. You need to understand locking overhead. You need to understand how your specific workload patterns interact with the allocator's internal structures. A one-size-fits-all approach is insufficient. Custom or heavily tuned allocators like jemalloc are essential for maintaining throughput and reducing garbage collection pauses. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.